All right, so this is the test 3 review. So you can fast forward and rewind to any question that you really still didn't get answered during class time. All right, so number 1 on the review has a circular spinner. It says find the probability of blue. Remember that the probability of anything is how many times what you want to happen goes on top, and then the total number of outcomes goes on bottom. So there are 3 blues out of a total of 10 sections. Okay, so that would be 0.3 if you were writing it as a decimal, or 30% if you're writing it as a percentage. Okay, on the test you need to be able to do all 3. You need to be able to write fractions, decimals, and percentages, so I'll try to do that for most of them. All right, number 2 involves a standard deck of cards. Okay, so the probability of red, 26 or half of the cards are red, or you could just jump to exactly half, okay? But either way, that's 0.5 or 50%. So you can either say there's 26 red cards out of 52 cards, or you can say red is 1 color out of 2, okay? Either way you want to do it. The probability of drawing a 4, there are 4 of every type of number/letter card, so that's 4 out of 32. That reduces to 1 out of 13, which is going to be about 0.0769, or about 7.69%. Part C, the probability of a red or a 9. So because there is a way for it to be both, remember the probability of or, which if you look on the back of your key, okay, this is the formula chart that you would get. And that's been uploaded also, so you can kind of pay attention to that. But it would be the probability of red, so let's take the unsimplified fractions, plus the probability of a 9, which would be 4 out of 52. But then you would need to subtract off the 2 cards that are red and 9. Okay, and so this is to avoid counting cards twice. So basically it avoids counting the red cards twice. The red 9s, I should say. Let me be more specific there. So remember, when you add and subtract fractions, if you have a common denominator, you leave that. And then you just add and subtract the top. So it would be 28 out of 52, which reduces to, put it in my calculator and do math fraction, 7/13, which is 0.5385 if you round it, or about 53.85%. D is the probability of the red of clubs, or red 9 of clubs. So if you know anything about cards, there is no red 9 of clubs. That's impossible, okay? Meaning that it is 0 or 0%. When something cannot happen, it's 0%. When it's certain to happen, it's 1 or 100%. 1 as a decimal, 100% as a percentage. The probability of 2, when you see this little symbol here, remember this means not 2. So you can do this a couple of ways. You could basically subtract off the number of cards that are 2s, right? So there are 52 cards, 4 of them are 2s, which means 48 of them are not. So this reduces to 12/13, which is about 0.9231, or about 92.31%. So for the test, you do need to make sure you know the basics of a deck of cards, just because that's a way that I can use kind of one topic and kind of ask a whole bunch of probability questions. So the probability of a heart or face card, so that U means or. So the probability of a heart or a face card. So first we need to count the hearts, right? There are 13 hearts. Face cards are anything with a face, so that would be any jack, queen, or king, so that would be 12 out of 52. Okay, but then we have to subtract off those that are both, so we need to subtract off the hearts that are face cards, and there's 3 of those. So again, if you leave the denominator the same and then you add and subtract the numerators, you get 22 out of 52, which reduces to 11 out of 26. And so that would be 0.4231, or about 42.31%. And then G, find the probability of the heart. When you see the upside down U, that means and face card. So for this, it has to be both. Okay, so a heart and a face card would have to be only the ones that are both heart and face card together. So that would be the 3 of the jack of hearts, the queen of hearts, and the king of hearts. So that's 3 out of 52, which is 0.0577 or 5.77%. So notice for all of these, it's always how many of the desired outcomes goes on top, and then how many total outcomes goes on bottom. H says, are the events drawing a card that is a heart and drawing a card that is a 2 mutually exclusive? Okay, remember mutually exclusive, we defined this way back when. Mutually exclusive means they cannot happen together. And so since you can have a heart that is a 2, they are not mutually exclusive. So they're not mutually exclusive because the 2 of hearts is both. Okay, so mutually exclusive would mean it would be impossible for them to occur together. The probability that a card is a spade, given that it is a 10. So the probability of spade, given that it's a 10. So remember, this is the formula where you need to maybe look at your formula chart. Okay, so the formula for something given something else can be found with this formula being rearranged. So it's always the probability of both over the probability of the second thing. Okay, so this is the probability of both over the probability of it being a 10. Okay, so the probability of a 10 of spades would be 1 out of 52. Probability of a 10 would be 4 out of 52. These do simplify. Since they're both over 52, that would actually go away. So you would actually get 1 out of 4, which is, of course, 0.25 or 25%. Okay, so remember that bar means given, given that. And then last but not least, the probability that the card is black, given that it is a club. So the probability of black, given that we know it's a club. So again, this would be the probability of both over the probability of the second thing. Okay, so the probability of both, so how many black clubs are there, right? So notice all of the clubs are black, right? So really the question is just how many clubs are there? So that would be 13 out of 52. And then the probability of club would also be 13 out of 52. So this one's kind of a strange one, kind of not that interesting. So you end up getting 1 or 100%. And think about that logically for a minute, right? If the probability is, we're trying to find the probability of black and we already know it's a club, well, all of them are going to be black, right? If we already know for sure that it's in the club category, then it's definitely black as well. Okay, so let's look at number 3. So a sample space for the sex of 2 kids. Sample spaces have curly braces, and then you just list all the possibilities. So the possibilities for the babies would be boy, boy, possibly girl, girl, right? You could have a boy followed by a girl or a girl followed by a boy. Okay, so notice there's 4 chances, or 4 choices, I should say. So the probability of at least one girl, notice that in this case we can just look at the sample space. Okay, so the probability of at least one girl, you just need to count the numbers of the options that have at least one girl. Notice there are 3 of them, so that would be 0.75 or 75%. All right, number 4. A bag contains 3 marbles, 3 red, 4 yellow, 8 green. So the difference with A and B is that A is with replacement. And I'm going to skip a little space, and B is without replacement. So that's the terminology we use when we put an item back versus when we don't. But for both of them, we actually have 2 events. So for this one, we have the first draw, and then we have the second draw. And because this is an and situation, I am going to multiply them. Okay, so let's talk about that. So the probability of green, there are 8 green and how many marbles? 7, 15. So 8 times 15. Notice we put it back, right, with replacement. So the second one's also 8 out of 15. When you multiply fractions, you just multiply top times top and bottom times bottom. And if you figure that out, that comes out to be 0.2844, or about 28.44%. Without replacement, we're going to do a similar process, right? So we're going to have the first draw here, and we're going to multiply that by the probability of the second draw here. So notice the first draw is not affected. The first draw is still 8 out of 15, but the second draw, we did not put the green marble back. Sorry about that, let me move it up. We did not put the green marble back, which means now there's only 7 green marbles and actually only 14 total marbles. Okay, so if you, this will be 56 out of 210, which reduces to 4/15, which is about 26.67%. So there it is, written as a decimal as well. Okay, so it does matter when you put items back versus when you don't. But notice in both cases we multiply, since we are finding the probability of one event and the other. All right, so number 5, a small combination lock on a suitcase has 3 wheels, each labeled with digits 0 through 9. If an opening combination is a 3-digit code with no repeats, what is the probability of guessing the right combination? Okay, so notice that we can't repeat the number. That's important. So in this case, we have 3 numbers, or 3 digits. So we have the first digit, we have the second, and we have the third. And again, we would have to get all of these right to be able to open the combination lock, right? So the first time you've got a 1 out of 10 shot because you got digits 0 through 9. But the second time, whatever number it is has been taken out, so you only have 9 choices. So you got a 1 out of 9 shot of getting the second one right. And then 2 numbers are missing, so the third one only has 8 choices. And so if you multiply this all out, you're really, really unlikely to make a random guess. So notice this is actually 0.0014. or about 0.14%. So actually considerably less than 1%. So you have a very, very tiny chance of getting that right. Okay, let's go on to number 6. So you might have some tables to read like you do on number 6, where you just have to kind of figure out what it's asking. Okay, so in part A, it asks for the probability of less than 10,000 miles or that they were in an accident. Okay, so remember that is the probability of the first thing plus the probability of the second thing minus the probability of both. Okay, so we're going to do the probability of the first thing, which if you read that, the less than 10,000 is a total of 0.25. Okay, we're going to add that to the probability that they had an accident. So if you look at your table again, the total that had an accident is 0.50. But then we need to subtract off anyone who's in both categories. Okay, so I'm going to kind of show this right here. So notice, this is where I got the less than 10,000. This is where I got the accident. But then we need to subtract off this, the people that were less than 10,000, and they had an accident, right? Because we don't want to double count those people. So we would subtract off 0.10. And so that's going to give us what's on the key, which is 0.65 or 65%. Okay, so this basically, this avoids double counting. So that's why we have to subtract it off. All right, so part B says, what is the probability a person drives 10,000 or more miles and has no accidents? So that's a little different, right? So this one is the probability of greater than or equal to 10,000 and no accident. So basically you only want the people who are in a specific category for this one. I think I kind of have a typo on my key, but what is the probability that a person drives 10,000 or more miles per year? Okay, so 10,000 or more is where you have to, oh no, actually it's all right. So 10,000 or more is actually both of these categories, and then you also want the no accident people. So it would actually only be this 0.15 and this 0.20, or 0.12 I mean. So it'd be 0.15 plus 0.20 or 0.35. Which is, of course, 35%. So note, I only counted the people that were in this category and no accident, or the 10,000 to 15,000 category and no accident, and then plus the people that were more than 15,000 and no accident. Okay. All right, so number 7. Note that in number 7, this is mentioned as a loaded die because not all values are equally likely. Okay, so for part A, remember that all probabilities must add up to 1. So that's how you're going to find the probability of 6, even though I didn't give it to you. Okay, so you're going to add up all the probabilities. So the probability of 6 would actually be 1 minus the sum of all of the values, right? And so if you sum all of those up, you should get 0.81, which means that this must be 19%. Okay, so how I got this was the sum of all the probabilities so far. So I'm going to say of 1 through 5. All right, so that's A. B says, what is the probability of rolling a 1 or a 4? Okay, notice you can't have a 1 and a 4 at the same time, so you don't have to worry about the subtraction principle where you have to take it off. It can't be both a 1 and a 4. So you just need to add the probabilities of 1, which is 0.20, plus the probability of 4, which is 0.118. 0.18, not 0.118. So you get 0.38 or 38%. The probability of an even number. So even implies that it's 2 or 4 or 6, right? Those are the only even numbers we have on a 6-sided dice. So again, that's very similar to part B. We just need to add those up. So if you add all 3 of those, you get 0.49 or 49%. Okay, so that's kind of the end of the basic probability questions. Then we start talking about tree diagrams and how to read them. So notice in number 8, I give you a tree diagram. I want you to know how to read it and how to answer the questions based on it. But then starting in number 9, I'm asking you to do your own tree diagram. So you need to make sure you know how to do both. Okay, so here's my tree diagram, right? And we're going to be referring to it, so you need to make sure you have your review out. So for number 8, one of the things is you need to make sure you know how to read these, right? M and A is how you read that. Okay, so the probability of M and A would be M followed by A. So it's like this path, M followed by A. So it would be 0.6 and 0.8. Okay, and when you have an and situation, you multiply them. So that would be 0.48 or 48%. Okay, so make sure you have your tree diagram out. The probability of N and A would be 0.4 followed by 0.3, and you'd multiply them again. So that would be 12%. The probability of A, notice we just found the 2 ways to get to A, right? So all we need to actually do is just add those up, okay? So we just need to find the probability of M followed by A plus the probability of N followed by A. So we would just take the 0.48 plus 0.12, and that would give us 0.60 or 60%. Part D, the probability of A given M. Okay, so remember the formula for that is, well, I actually don't really need a formula. So this is the probability of A given M. So in other words, we're already here, and then we want to know the probability that we then go here, which is actually just 0.8. There's actually no figuring to do there. 0.8 would be 80%. However, the second version of that, where I know the end result, but what I don't know is if it came from A or not. So notice, here's the difference, right? I want the probability of M given that I ended up at A. So I know my conclusion. What I don't know is where it came from, okay? So anytime you, when you know the conclusion, so not when you're trying to find the conclusion, but when you already know the conclusion, you need to use that Bayes theorem that we talked about. And that formula is on your formula chart. And Bayes theorem just says that it's the probability of both over the probability of the second thing. Okay, so it's the probability of both M and A, which we already did that, right? That was 0.48 times the probability of A, and we actually already did that, right? That was 0.60. So if you work that out, you get 0.8 or 80%. And then part F says, are these events independent? How do you know? Okay, so this is how you know. Remember, we did a couple problems like this, but basically we need to prove that the probability of A times the probability of M given A is the same, and I'm going to put a question mark, as the probability of A and M. Okay, so that's what we're trying to prove, basically. So we would, sorry, that's actually not quite right. Actually, this is what we're trying to prove. This is an easier way. So what we're trying to prove is that the probability of A equals the probability of A given M. Sorry about that. So I'm going to put a question mark here because we're not sure that's true, because we have all of these values, and that's why I want to do it this way. So notice the probability of A is 0.6, and that does not equal the probability of A given M, which we got to be 0.80. Okay, so since those aren't equal, then no, they're not independent. It's kind of a double negative. What that means is that they're somewhere related to each other. Okay, independent means the results of one don't affect the results or the outcome of the other, which means they are some way dependent on each other. But we don't really have to talk about how much they're dependent. It's just that they are. For number 9, you would come up with your own tree diagram. So we've got 2 groups of employees, male and female. Okay. Notice there are 320 males. If you add the males and females together, you get 600. So 320 out of 600 is the males. 280 out of 600 are the females. And then you have employees that are either on the flex schedule or not. So I'm going to use that not notation where you put the 1 there. And then the same with the females. They can be on flex or not. And you can fill these in too. So notice 160 of the men, right? So 160 of the 320 men are on flex, which means all you'd have to do is subtract these two to figure out how many weren't. So this one actually comes out to be the same. Now, you could definitely reduce these fractions. For instance, these both reduce to 1/2, okay? But I'm just gonna leave them as they are because you don't have to reduce them to make this work, so I'm not going to do it. And then 190 of the 280 women are on the flex schedule. And then if you subtract those, that means 90 are not. So notice that every branch of the tree diagram adds up to 1. These add up to 1. These add up to 1. And so do this, these. You need to make sure of that every single time. Okay. But then I think we can answer the questions. So, or actually just the question. Okay. So the probability of male, so the probability the employee is male given that we know they're on flex. Okay, so by the way, notice that we know the outcome, right? We know that they're on flex, so that means we need to use Bayes' theorem. So it's going to be the probability of both over the probability of the second thing. Probability both of male and flex, in other words. Okay, so let's kind of look at what that is. You can do a lot of simplifying here, or you can just kind of enter it in as it is. So the probability of both would mean we're going to go here and then here, right? So that would be 320 out of 600, but also times 160 out of 320. Okay. Notice if you wanted to, you could simplify this fraction like that. You don't have to, but you can. You actually could simplify 160 over 600 a little bit more too, but we're not going to worry about that. The probability of flex, notice there's 2 routes to get to flex, right? You can be male and be on flex time, or you can be on female, or you can be female and be on flex time, so we need to add the 2. So that's going to be 320 times 600, or divided by 600, times 160 out of 320. That's this route, and then we need to add it to the possibility that the employee was female but was also on flex. So notice I did this times this plus this times this, both ending in flex time. So again, we have a lot of simplifications we can do here. You can either do them or not. It really doesn't make much difference to me. But when you reduce it using your calculator, you should get 16 out of 35, which is right about rounds to 0.4571 or 45.71%. Okay. So number 10 is similar. Okay, we need to create our own tree diagram. So notice we have 3 plants in this one. We have, or 3 machines, I guess. So we have machines A, B, and C. And 40% come from here. 35% come from here. And 25% come from here. Notice those add up to 100, okay, or 1 if we're in decimal format. And then we have the possibility that the piece is, or that the part coming off the machine is either defective or not. So I'm just going to use letters here just because I don't want this to get very crowded. So this one has a 1% chance of being defective, which by default means 99% are not defective. That's machine A. Machine B has a 1.5% defective rate, which means that 98.5% of them are fine with no defect. Watch your decimal place there. And then the last one, 2%. So 98% of them are okay. So I'd want you to be able to complete the tree diagram and then answer the last question. If you know it's going to be defective, what's the probability that it was produced on machine B? So what's the probability of B given that you know it ended up being defective? So notice, I already know the outcome, right? I know that it was this, this, or this. I just want to know what the chances is that it came from this plant instead of the other 2 plants. Okay, so this is Bayes' theorem. One more time, we're working backwards through the tree diagram. So it's going to be the probability of both over the probability of defective, the second thing. So the probability of both would look like both B and defective, right? So it would look like 0.35 times 0.015 on top. But then as far as the defective goes, there's 3 routes to get to defective. You could go here and here, here and here, or here and here. So we actually need to add all of those up. So it's going to be 0.40 times 0.01 plus 0.35 times 0.015, and then plus 0.25 times 0.02. Kind of ran out of room there. So if you work all of that out and simplify it, you'll get what's on the key, which works out to be about 0.3684, or about 36.84%. Remember, if you're going to put this in the calculator, anything with more than one piece you want to surround with parentheses. So we would want parentheses around the top and a parentheses around the bottom. You would not need necessarily all these parentheses around the decimals. I just wrote them like that so that we wouldn't have multiplication dots and decimal points at the same time, because that can get kind of confusing in the way that that looks. Okay. Number 11, expected value. Okay, so expected value is one of the formulas that's on your formula chart. Expected value is a weighted mean when the values aren't equally likely. Okay, and notice 3 houses sold, 4 houses sold, 5 houses sold, those aren't the same probabilities across the board, right? So 3 houses sold, there's a 10% chance of that. 4 houses sold, there's a 13% chance of that. 5 houses sold, 20%. 6 houses sold, 25%. 7 houses sold, 20%. And then 8 houses sold, 12%. So if you add all of the, or multiply all of those up rather, then it's basically 5.68. So this is 5.68 home sales per month. So rather than adding up all the numbers and dividing by however many numbers you have, that doesn't make sense in this problem because they're not equally likely. You are actually most likely, if you look at your list, to sell 6 homes in a month. Okay, by the way, that is why your average kind of hovers pretty close to 6, because that was your most likely option. So you'll probably have a mean, median, and mode question on the test. Okay, so I don't expect this to be too bad. So I'm just going to kind of quickly run through it. Remember, mean is always the sum divided by how many values you have. Okay, and so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 values. So if you add all of those up, I'm not going to do that for you, but I already kind of did it ahead of time. It's 1360 divided by 20, you get 68. Okay, remember the median is the middle once values are ordered. So you do need to put them in order first, okay? And if you put them in order first, there are actually 2 tied for the middle. And so if you put them in order, and I kind of had to do that off to the side, it looks like 70 and 75 are going to be tied for the middle. So you average those, and you'll get 72.5. Okay, so when there's one clear middle, then that's the median. But when there's 2 tied for the middle, you average those 2 middles together. And then remember that mode is just the most frequent. So you would just need to, again, look at them, but the mode would just be 80 in this case. 80 is the value that's repeated the most number of times. Okay, so let's talk about number 13. I'm not going to punch in number 13, but I'm not going to show it all worked out on the calculator. But first it says find the probability distribution Actually, no, it doesn't. It just asks for the standard deviation. Sorry, that was an old question. So you need to remember your formula. So this is how you find standard deviation of a small sample set. You do the square root. Now you can do this in table form. We did one like that. Or you can do like, first you need to find the mean. Okay, so I guess we need to talk about that. So the mean would be whatever you get when you add up all the times. And then divide by the number of values you have. So I don't want to spend too much time on it because I feel like you should be able to get the mean. But then the standard deviation is you take the first value, which is 53, minus that average squared, and then you add it to the next value you have minus that same average squared. And then I'm going to say dot, dot, dot here because you're going to do that for all 8 values. And then you're going to divide that sum by n minus 1, or 1 less than the numbers that you have. And then you should get this value. So I really want you to check this on your own. So you should get 9.46799 seconds. Okay, so on the test, I probably won't give you one with 8 values. I'll probably give you one with a smaller number of values, but you definitely need to know this process. So it's always find the mean first, okay, and then it's value minus mean, parentheses squared, plus the next value minus the mean, parentheses squared, plus blah, 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 so on and so forth, divided by the number of values minus 1, and then take the square root of the whole thing. Okay, so you might need to go back on the day we did standard deviation. It was the same class day, I think, that we did expected value, but you might need to go back and look at that note set to make sure you're solid there. So 14 is similar. So first you would need to find the mean. So we'll do that first this time rather than writing it off to the side. So you would do the sum and then divide it by 1, 2, 3, 4, 5, double 10 values. So I'm going to let you do the mean, but you should get 98.44. And so then the standard deviation is again going to be the square root of the first value, 98.6, minus this mean, squared, plus the second value, which is also 98.6, minus 98.44 squared, plus the third value, minus 98.44 squared, plus dot, dot, dot for all 10 values, okay? And then we're going to divide that by the number 10 minus 1 because there's 10 values. So again, I will ensure that it is something a little more pleasant on the test. It'll have much less values, but you should get this when you work it out. So you really need to make sure that you can do this full process. So I'm not showing you every little step because it would just be tedious to write out, but you would do that mostly on your calculator. Okay, you need to make sure you know how to do normal distribution. I will give you the hint that I gave you before, number 15, on the test. So within one standard deviation, we'll cover 68% of the values in a normal distribution. Within 2 standard deviations, we'll cover 95% of the values. And within 3 standard deviations, we'll cover almost all, or 99.7% of the values. So everything we'll do about normal distribution will have something to do with these 3 quantities, and you're definitely going to need to make sure that you know those, okay? Or know how to use them, I should say. So let's look at number 15. 95%, right? So 95% is supposed to be significant to you because it means within 2 standard deviations. Okay, so it says assuming this data is normally distributed. So when you see the term normally distributed, you need to draw you a bell curve. Okay, remember the mean goes in the middle. The bell curve peaks in the middle and then it kind of falls off after that. And notice, because of the 95% statement, we know we're supposed to go out 2. And we know that when we go out 2, we hit 62 and 90. So we just need to figure out what would need to go kind of halfway in the middle. So if we want to know the mean, we can literally find the mean of 62 and 90. So if you add those up, you will get the middle ground, which is 76. So this is 76, which means this goes here. Okay, so let's talk about it. By the way, this is 14 less than 76. This is 14 more. Okay, so for this to all be kind of equally spread out, it looks like every section is actually 7 wide. So this would be 83, right? 7 more than 76, and then 7 less than 76 would be 69. Notice that everything's equally spread out. 7 apart, 7 apart, 7 apart, 7 apart. Okay, so that answers part A. The mean or the middle was 76, and the standard deviation was how far away each section was from each other, and that's 7. Part B says to tell how much is between 55 and 97. So notice those aren't even marked yet, right? But notice if you go out one more set of 7, you're going to be at 95 to 97, okay? So notice that we're going out 3 in both ways, right? So this is supposed to be 99.7%, right? That's what we have up here. So the answer to part B is actually just 99.7%. But C is a little different, right? We want the probability that we weigh between 62, so that's here, and 83. And notice it's not like evenly spaced from the mean. Okay, so there's all different kinds of ways to do this. What I did is I figured that I knew from part A that between 62 and 90 was 95. And then I just needed to subtract off this little wedge here, okay? And I got that by figuring that it was halfway between these two, right? And these two would be, so notice like here to here, one standard deviation is 68, right? Here to here is 95%, okay? So I can take 95% minus 68%, but then divide it by 2 because it's only 1/2, okay? You also remember, I'm just gonna give you a memory jog here, you also could separate these out into strips and figure out what the strips would be, right? So for instance, I'm gonna just do a couple of them. This would be 34%, and so would this because they're exactly 68%, and then we went out from there, okay? So you also could do it that way. But however you want to slice it, it should give you 81.5%. Okay, so number 16 is similar. Okay, so we have a normally distributed data, right? The mean goes in the middle. And we kind of curve our normal curve from there. Okay, it tells us the mean this time, so that's 3.1. And then it tells us that the standard deviation, sorry about that, is 0.005. So I'm going to use a different color here because it's a thinner marker. So I need to go out 3 standard deviations on both sides, and then I just need to add and subtract the 0.05 every time. So this would be 3.105. This would be 3.110, and this would be 3.115. I got all of these by just adding 0.005 every time. And same thing over here. We will get 3.095 here, 3.090 here, and 3.085 here. Okay. So notice now it's asking us about 99.7%, and we know that 99.7% is within 3 standard deviations. So now that I have a good bell curve, I just need to figure out what those two values are, right? So it's going to be between 3 out this way, which would be 3.085 meters, and then 3 out this way would be the 3.115 meters. Okay, so the last few questions are graphing questions. So I'm going to try to see if I can get them in on this single video. I can only video an hour at a time, so I'm going to see if I can kind of squeeze this in kind of quick. All right, so number 17 says graphically find the solution to the set. So you do need to make sure you know how to figure out how to graph these things. So I'm going to kind of shorten this up a little bit, and you're going to need to make sure that you can go back and look at it yourself. But equation number 1 starts off looking like 3x minus 6y is less than or equal to 12. If you solve for y and you remember all your rules, you would subtract 3x from both sides. You would divide by negative 6, which means you're going to have to flip the inequality sign, so you should get this. Okay, so I'm going to kind of graph as I go here. So maybe this Post-it note wants to work for me. I don't know why it wants to go on crooked. All right, so this means we have a y-intercept of -2, slope of 1/2, up 1 over 2, up 1 over 2. So this line is going to look kind of like this, right? And we want to go greater than, which means we're going to be shading this way. Okay, equation number 2 starts off looking like negative x plus 2y is less than or equal to 4. Okay, so again, you would add x to both sides, you would divide by 2, so you should get y is less than 1/2 x plus 2. So I'm going to graph that with a different color, maybe. So notice this has the y-intercept at 2, up 1 over 2, up 1 over 2. Okay, so we actually have parallel lines here, if you can notice, and we're shading this way. So when you get to the shading part, remember, you also want to stay above the x-axis and on this side of the y-axis, because if you look, you also have the requirements that x and y have to be positive. So try not to smear this. So the graphic solution would be any point in the shading. So the solution is any point in the shading. Okay. So that's what that one should look like. Number 18. Number 18 is where you start using, oh, by the way, it also asked in number 17 whether it's bounded or unbounded. And notice this is unbounded because it goes on forever here. Like this shading here would continue. So it's bounded here on these corners, but it's not bounded over here. So if it's unbounded anywhere, it's considered to be unbounded. Okay, so number 18 is similar to number 17, but it just takes it a step further. You have to graph, but then you need to figure out where the corners is to try to find out what equation you have. So if you want to maximize the profit, which is 2x plus 3y, but you have the following restrictions. Okay, so the first restriction is 2x plus y is less than or equal to 12. Okay, so if you solve that one, just move everything over, right? This would be y is less than or equal to negative 2x plus 12. So let's graph that one first. So 12, I've got 2, 4, 6, 8, 10, so I'll just go up a little bit more to find 12. So I've got 12 here, and then I go down 2 over 1, down 2 over 1, and so on and so forth. Okay, so I would down 2 over 1. I need to make that a little steeper because it needs to go here. So anyway, I think you kind of see the point. It's going to need to cross the x-axis at 6. So I kind of had to fix it there. And then we would be shading under. And then the second equation, which starts off looking like x minus 2y is less than or equal to 1. If you move everything over, and you are going to have to switch the inequality sign here too, you would subtract x you would divide by -2. So you should get the equation y is greater than or equal to 1/2 x minus 1/2. So that means it crosses the y-axis at -1/2, and then we go up 1 over 2, up 1 over 2, up 1 over 2 here. Okay, so it can be a little difficult if your graph isn't super perfect, but you would graph that. I think mine is close enough, and then you would be shading this way if you pick your test point. So it's a little subtle, but you actually have this for your section, but make sure you cut it off at the x-axis because we also have to keep x and y bigger than 0. So here is where you now compare the corner points. This is the method of corners, and then you plug them into the profit equation. So the corner points, and again, you have to be careful. There's one little subtle one you might not see. So 0, 0 is here, but this is actually a corner point too. It's 1, 0. And then the point where they cross each other looks like 5, 2. So you would need a really good graph, and then up top it's 0, 12. So you plug all these points in. So this one you get 0. That's not expected to be the high. This one would be 2 times 1 plus 3 times 0 or 2. This one would be 2 times 5 plus 3 times 2 or 16. And this one would be 2 times 0 plus 3 times 12 or 36. So notice for this one we're trying to find the max. Okay, if you were trying to find the min, you would find the smallest one. But here is the biggest one. Okay, so that's how I got the answer. That's on the key, which means the maximum profit is 36 when you have x is 0 and y is 12. Okay, so the max is p equals 36 when x is 0 and y is 12. Let's go ahead and write that out because you'll want to do that on the test. Okay, so the last two equations, which again I'm going to try to kind of squeeze in here. Let's see if I can make it. So you need to come up with your own equations. So the first one is, sorry, I gotta get my papers right here. So the first one is we have two products, okay, and so we want to maximize the profit of those products. So if you read the problem, the first one is 30 per item, the second one is 40 per item, so that's going to be our profit. But then we have some restrictions, okay, so it says that we only have a cost of 100 for the first one, 150 for the second one, and we have to stay under cost of 600,000. One more zero. Okay. And then also it says that we have to stay under 2,500 items. So the cost has to stay under our max cost and the items has to stay under 2,500. So notice we also have this implied, right? X and Y would need to be bigger than 0. So for equation number 1, we're going to use, because these numbers are so big, we're going to use the intercept method. So here we've got 100x plus 150y equals 600,000. So we'll find the x-intercept, as always, by setting y equal to 0. So if you set y equal to 0, you're going to get x equals 6,000. So I'm not going to show every little step here, but I think you can fill it in. For the y-intercept, you would set x equal to 0. And if you do that, you'll get y equals 4,000. So let's go ahead and graph what I have so far. Okay, so I need to cross the y-axis at 4,000. I need to cross the x-axis a little further out at 6,000. Okay, so this is equation number 1, and I'm going to shade under because it's less than. Okay, so let's take the second equation, x plus y equals 2,500. Okay, so notice this one's kind of not that interesting, right? The x-intercept would just be x equals 2,500 if you set y to 0. The y-intercept would just be y equals 2,500 if you set y to 0. But maybe what is a little interesting is how the graph's going to look. So notice 2,500 would be about here-ish, and maybe about here-ish. I'm just kind of eyeballing it. Okay, so when you go to graph these, notice you only care about where they overlap. So actually these don't cross each other, and we're really only concerned with this overlapping area here. In other words, this outer equation is actually kind of insignificant here. So when you go to try to figure out the points and compare those with the profit equation, you actually only have 3 corners in this one because it's just a triangle. So you have the point 0, 0, you have the point 2,500, comma 0, and you have the point 0, 2,500. So here, this is going to give us a profit of 0. Nothing interesting going on there. This is going to give us a profit of 75,000 if you plug in all the values. And this is going to give us a profit of 100,000. Okay, so this is, we need one more 0. This is the max, right? So the max profit is 100,000. For 0 units of product A and 2,500 units of product B. In other words, they really should not focus any of their attention on product A. They should actually just focus all of their resources and time on product B because it's making them more money. Okay, so last but not least, and we're going to try to squeeze it in. So we have that we want to maximize yield. Yield is just interest, or how much the account yielded. So the yield equation is going to be 6% for the bonds, and then 10% for the stocks. Okay, but then we have some restrictions, right? They only have 24,000 to invest. So X plus Y, stocks and bonds can't be any more than 24,000. And then it says that the bonds has to be 3 times the stocks. So the bonds has to be at least 3 times the stocks. And then of course we have X and Y have to be greater than 0. So kind of an interesting equation this time. So X plus Y, and sorry, not equals, right? We would have to say less than or equal to, because we don't have to invest all the money, but we can't do more than 24,000. So X plus Y equals 2,400. Notice that when I come down here to find intercepts, I just use an equal sign, but really it's really less than. So the x-intercept is going to be X equals 2,400. The y-intercept is going to be Y equals 2,400. Okay, sorry, 24,000. Zeros all around. So let's go ahead and graph that. So I've got 24,000 here and maybe 24,000 here. And note that I want to stay this way. Okay. But when I try to look at equation 2, it's not really the same as what I'm looking for normally. Okay. So notice I start off with X is greater than or equal to 3Y. So rather than finding the intercepts, because by the way, they're both going to be 0 and not super helpful, I'm going to go ahead and rewrite this as a y equation. So this is actually y is less than or equal to x over 3, or y is less than or equal to 1/3 x. And if you're wondering why it's less than, it's because you have to read it backwards from y. It's like y is less than blah, blah, blah. So when you go to graph this, this means the y-intercept is at 0. And the slope is 1/3. So it's going to do like something like this, okay? And then by the way, we are going to be shading this way. So we know we're going to need to shade here. But the question is, how can we find the intersection point here? Okay, and so all we need to do is somehow combine this equation and this equation together to make that happen. Okay, so basically what we're going to do is see if we can figure out what the equation would need to be. Okay, so we can do a couple of things here. We can pay attention to this original equation. Okay, so I'm going to rewrite this as x minus 3y is greater than or equal to 0. Okay, because when I try to find the intersection point, That's what I'm going to need to do. So the intersection point is going to be what I get when I combine x plus y equals 24,000 and x minus 3y equals 0. Okay, so then I would notice I could actually get rid of the x here if I multiplied that by -1. So I'm going to finish this on video 2.